Hello and welcome. This video demonstrates clearly how easy it is to solve op-amp problems using superposition. This op-amp circuit is rather daunting for new students who are dealing with op-amp questions. It's actually a difference amplifier. Now, by superposition, we can ground one input and observe the response from the other input. In this example, we have V2 replaced by a connection to ground. So essentially, the plus terminal of the op-amp is grounded through R3 and R4 in parallel. We apply the voltage V1 and we see that our output, VO, when we have V1 applied, is the formula we would normally expect when using the op-amp as an inverting amplifier. I haven't derived the formula, I've simply put it down. Now we go and we look at the other input. This time we ground V1 so that the negative input of the op-amp is connected to ground through R1, and we apply V2 through a voltage divider into the positive input of the op-amp. So we see that the output for V2 alone is the normal formula that we can derive for op-amps when we connect our input to the positive terminal, only that V2 is reduced by the voltage divider as shown. Study it carefully to make sure you're happy thus far. So we have two output responses, one from V1 and one from V2. And all we have to do is algebraically sum them to get our total response. So as you can see, our final Vout is the sum of two terms, as shown. Now we'll see that that is absolutely the easiest way to solve this type of op-amp problem. We shall now proceed to do it another way. I've written the first term there at the bottom, and that expression that you see is for the current through R1. Let us examine that in more detail. Once again, the V2 is reduced by the voltage divider at the plus input. By the ideal op-amp property, we have the same voltage on both the plus and minus input. So one side of R1 essentially is the voltage contained inside of that pink circle. So we're taking the difference in voltage across R1, we're dividing it by the value of the resistor, and that gives us a current term. I equals V over R by Ohm's law. Okay, now we take the next term, which is the current through R2. And the current through R2 has to be equal to the current through R1, because no current can flow in or out of the negative op-amp terminal according to the properties of our ideal operational amplifier. So essentially, the current is the same through R1 and R2, and you should be able to be quite comfortable with our equation, which is a starting point for some algebraic manipulation. Now, I've reproduced the equation here at the top of the board, and we are now going to rearrange and solve this equation to get it into the same form as we got with the superposition. First, we are going to get rid of the R1 and the R2 in the denominators. Next, we are going to remove the brackets and multiply by -1 throughout so that we can have VO as a positive term. Study these expressions carefully to make sure that you can do the algebra. It's quite simple algebra, but some people, particularly new students, find it to be quite challenging. Next, we want to transfer the term and extract the common factor so that we have isolated VO. Notice we have isolated VO on the right. We've transferred that term to the other side, and we have extracted it out so that we have that. Now we reproduce that here, and we're already seeing that it's very similar to what we derived with the superposition. So we put back the superposition term, and we rearrange our expression, and we see that they are identical terms. So you can do it by algebra using KVL, KCL, and the OpAmp principles, or you can just plug it in to the expressions and use the superposition. But we're not done yet. We do not need 4 separate values of resistors. That's ludicrous to have 4 different values of resistors. For this circuit to be useful, we need to make R1 equal to R3 and R2 equal to R4. If you go back and study the diagram, you would see that makes perfect sense. Now, when we make R1 equal to R3 and R2 equal to R4, nice things begin to happen to our formula. As you can see there, we have ended up with 2 terms, V2 times R2 over R1 minus V1 times R2 over R1. And once again, when we extract the common term, we have what we actually wanted. We have the gain of the amplifier, and we see that it is amplifying the difference between V2 and V1. Thanks for watching the Stephen Mendes channel, and we'll see you in the next video.